Hi everyone, welcome back. In this section we're going to take another look at optimization problems. Specifically we're going to be interested in finding the maximum and minimum values of a function where we're restricting ourselves to a portion of the domain. These are called constrained optimization problems. Now we have seen an example of this back in section 14.7, but I didn't call it as such. But let's have another look at this example. So we had a wooden box and we wanted to create it so that it had a fixed volume of 32 cubic meters, but we wanted to minimize its surface area. So here we were interested in this surface area function, which is a function of 3 variables, but we were interested in only finding the minimum of this surface area function where our 3 variables had to satisfy this condition that x times y times z was 32. So this is what we call a constraint, because we're not interested in finding the minimum value of s over the entire set of points x, y, z in the domain of s, because that would be all of our 3. No, in particular we're interested in finding the minimum value of s for which x, y, z is equal to 32. So this problem we decided to attack using the techniques of section 14.7 by converting it to a optimization problem in 2 variables. So the way we did that was we took our constraint and we rewrote it. We rewrote it so that z could be expressed in terms of x and y. Then we plugged that into our function of 3 variables and constructed a function of 2 variables. And in this case, we are interested in finding the minimum value of s where x and y were both positive. So this just became a regular optimization problem. We found the partial derivatives, set them to 0, found the critical points, and so on and so on. What we're going to do in this section is we are going to, instead of solving for one of the variables in terms of the other ones and plugging it into the original expression, we are going to work specifically with the function of, in this case, 3 variables, and then keep on the side the constraint. And we'll work with those 2 in tandem with each other. So this is known as the method of Lagrange multipliers. Before we get into that, though, I want to again revisit this problem of the rectangular box optimizing. In this case it'll be cost, which is related to surface area, but slightly different in this case. So we're going to find the dimensions of the box that minimize cost subject to a constraint. The volume has to be v, some fixed constant. So we'll do this in the way we did that last example in 14.7, but then we'll also introduce this new technique of Lagrange multipliers and see how we can do it in this new way. Okay, so let's do this in the way we did it for section 14.7. So first we'll give some labels to our dimensions, x, y, and z. We know that x, y, z, the product of them, has to be v, that fixed volume. And what are we interested in? We're interested in the cost. So we want to minimize the cost. What is the cost? The cost is going to depend on x, y, and z. And what we see in the statement of the question is slate costs 5 times as much as glass. So glass is going to make up the 4 sides, slate is going to make up the bottom, and we're imagining it's open top because that's a different kind of material. For the top of plastic, substantially cheaper than the sides and the base, so we'll ignore the top for now. So what is our cost going to be? Well, the cost of the base has area xy, and it's going to cost 5 times as much as the glass. So if we imagine the glass is costing $1 per unit area, then the base would be $5 per unit area. So we're just going to run with that. So it would be 5 times xy plus, and then we've got a couple of sides to deal with. We've got the side with dimensions xz, so that's the front and the back. So we've got 2 of those, 2xz, plus 2 of the YZ sides. And so that accounts for all the sides. And then there's the top, but we're imagining that we're not interested in the top. It's made of a different material. So there's our cost function. We've got our relationship between our variables x, y, and z. We can use that to write z is equal to v over x, y. And we can plug that into our costs. So maybe before we do that, we can think, what are we actually interested in doing? We want to find the minimum value of the cost where x times y times z is equal to v. So of all the possible cost values that come out for putting in different values of x, y, z, we're only interested in the x, y, z values whose product is v, and we want the minimum cost to come out of this function. So we want to minimize the cost subject to this constraint. The way we're going to do that is we are going to create or change to a 2D optimization problem. So the way we're going to do that is we're going to look at this as a function of two variables. It's 5xy plus, and we're replacing z with v over xy. So this is 2v over y plus 2v over x. And what we want to do is we want to minimize this function. So we want to minimize c, where x and y are allowed to be anything bigger than 0. So now this is our 2D optimization problem. Find the minimum value of this. How do we do it? We find the critical points first. So we find the critical points. These are going to be the places where the gradient is 0. In other words, the two partial derivatives have to be 0, so that's equivalent to saying that the gradient is the 0 vector. The x partial being 0, that means that 5y minus 2v over x squared has to be 0. And we have that 5x minus 2v over y squared is equal to 0. So that's the x partial and the y partial equal to 0. This means that 5x squared y is equal to 2v, and 5xy squared is equal to 2v. So we need to solve these two equations for x and y. What we can do is we could divide the first equation by the second equation. That gives us that x over y is equal to 1, or in other words, x is equal to y. And we also then have one of these equations. I'll take the first one, for example. When x is equal to y, we also have that 5x cubed is equal to 2v. Or in other words, x is equal to the cubed root of 2v over 5. So therefore, we have that x is equal to y is equal to the cubed root of 2v over 5. So there's our critical point. Due to the nature of this problem, this has to be where the minimum is. So maybe think about, why do we know it's a minimum? Well, I could make this a really expensive tank. I can make it a really expensive tank by just taking the base as large as possible. Now, because my volume is fixed, if I make that base as large as possible, that is, make the x and y values as big as possible, I can always balance that off by taking the z value as small as possible. So I can make a really big base tank that is of tiny height, negligible height in some sense. And that's a perfectly good aquarium that has a volume of v. I shouldn't say perfectly good. It's a theoretical aquarium that has volume v, but it's probably not a good choice because it's going to be so big in the base and so small in the height. But nonetheless, such a thing exists, and that means that finding the minimum value of this cost function, well, I can make the cost function as big as I want. So if I do find a critical point, it's got to be the minimum. And so I have found a critical point. And so therefore, we have that the cost is minimum when x equals y equals the cubed root of 2v over 5. And the cost at, oh, and maybe I should say, and then the z value, because we can work out the z value now. We have that z is equal to v over xy, so the z value is going to be 25 over 4v to the 1/3. And I think that's all we need. Yes, find the dimensions. There we go. Find the dimensions of the aquarium that minimize the cost of the materials. So we found the dimensions. X and y are the same, so we've got a square base, and then we've got our corresponding height. So again, the key idea here was we converted this to a 2D optimization problem and used this idea of critical points. Now, what we're going to do is we're going to look at how we can solve this problem in a different way using this idea called the method of Lagrange multipliers. So here's the setup. Suppose we have a function f of x, y, z. That's the thing we're trying to optimize. And we've got this other function g. G is going to be our constraint. Then if the max or minimum value of f, subject to the constraint that g of x, y, z equals k, occurs at a point P, then we have that the gradient of f has to be a multiple of the gradient of g. In other words, the gradients have to be parallel. Okay, so let's think about this in terms of a picture, and then we'll come back to what the statement says above. So the picture below is, I've dropped the dimension by 1 just for ease of visualizing this, but the idea is we've got this function, f of x, y. And I'm interested in trying to figure out where it's biggest and where it's smallest. But not just on its entire domain. I'm interested in if I only put in to f points that live on this curve, g of x, y equals k, so that orange curve there, then at what point on that curve g will my function value f be as big as possible? So I start putting these values in. And so for example, if I put that value in, we can see what the function value is. It's going to be 7 because it's on the level curve, f of x, y equals 7. If I put some more values in, I can see, oh, at that point it's going to be 8. If I put a value in somewhere in between, that'll probably be around 8.5. So I can see that from this picture, I know for various points along my constraint curve what my corresponding function value is. Let's just think about this point down here. Maybe I'll put it in a different color. I'll put it in a red. Let's think about that point there. Could my function little f have a maximum value at that point? And the answer is no, because I have that curve with points on either side of the level curve. So for example, this orange point that's above the red point, it's sitting on the side of the level curve, f equals 8, which is the higher side. So I know that point over there is going to have a function value of like 8.5 or something more than 8, whereas the orange point that's below the red point has a function value that's lower. So I know not only is this point not a max, it's also not a min because there are points nearby that are lower. So what this means is that if my constraint curve ever crosses, and I'll draw the crossing in here, if it ever crosses one of the level curves, then I know that can't correspond to a max or a min because there are points on either side that are both above and below it. So in order to have a hope of being a max or a min, I've got to come up to the curve, one of the level curves, have a point, so there's a function value of 10, and then I got to turn around and come back the other way. And if we express this in terms of points of tangency, then what we have is that my level curve has to be tangent to the constraint curve. So here's my level curve. I'm drawing it in blue. And then here's my constraint curve. And they got to be tangent right at that point. I can't have one cross the other one. If I have the constraint curve cross the level curve, then there are points on it that are going to be higher than that point on the level curve. And on the other side, there'll be points that are lower. So they've got to be tangent to each other. But what that means is, since they're tangent to each other, it means the normal vector to the orange curve and the normal vector to the level curve have to be parallel to each other. So what we have is that at a max min of f on the constraint curve, g is equal to k, the curves, and by curves I mean the constraint curve and the level curve, have to be parallel. So they have to be, maybe we'll say, have to be tangent to each other. So their normals are parallel. But remember, what are their normals? The normal to that curve g equals k, that normal is going to be the gradient of g, whereas the normal to the level curve is the gradient of f. And so if their normals are parallel, it means that the gradient of f has to equal some multiple of the gradient of g, where lambda is just whatever the multiple has to be in order for them to be equal, because they're parallel to each other, so one is a multiple of the other. And so that's the method of Lagrange multipliers. It says you want to figure out where f is biggest or smallest if you restrict your inputs to live on the constraint curve. Well, you just look for the places where the gradients are parallel to each other, where one gradient is a multiple of the other, because that's going to be the places where you can have your max or minimum. They can't occur anywhere else. And so let's have a look at a demo of this. So here we've got our blue surface is basically our function z equals f of xy, where xy is allowed to be basically anything in the xy plane, so full domain of R2. But now we're interested in, what if we restrict our domain to f to only be this green curve in the plane? So that's our constraint curve. This green curve down in the plane below is our constraint curve. And so now I'm interested in what is the maximum or minimum value of f given that constraint. And so what I've done is I've taken all values of input that live on that green curve, plugged them into our function, and plotted them as that black curve up on our surface. And so now I'm really just interested in what are the maximum and minimum values along this black curve. And we can start to see this. I mean, we can angle it around and see, okay, I'm staring at a local max there because I'm coming up, 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 and then down, 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 down. So there's a local max somewhere right around here. Let's go ahead and look at the gradient vectors plotted to the level curve at that point and also the level surface at that point. So what I've done down below is, for that black point on the surface up above, I've looked at where it's coming from in terms of what point on the constraint curve is being put into the function to give that black point up on the surface. Whatever that point is, I've taken also the level curve that's up on the surface, and that's this black sort of ellipse down in the plane below. So that is all of the points on the surface up above, all the inputs that give that same height. So that's the level curve on our surface, which has the same height as the black point on that surface. So if I move that black point around on the surface, I'll get different black curves down below because those are the level surface, or the level curves that have the same height as that black point. So now, the idea is as follows. Let me just drag the point around, maybe put it somewhere around, let's say right about there, for example. Now, if I ignore what's going on up on the surface and just focus down in the plane, what can I see from this? Well, I can see that I'm at a point on the constraint curve, because this black point in the plane down below is on the green curve. But if I move on either side of that point along that constraint curve, then what do I notice? Well, let's say I go up a bit along that green curve. If I go up a bit along the green curve, then I'm inside the level curve, the black curve. Remember that black curve consists of all points that are the same height up on the surface. So they're all inputs that give the same output. And so this tells me that if I move away on the green curve a little bit, then what I get is values that aren't going to be the same height. In fact, we're inside the level surface, so these are going to be values that are lower. Whereas if I go in the opposite direction along the green curve, I'm outside of that black curve, that black level surface. So I'll have values that are higher. And we can see that on the surface itself now. If I look on the surface, if I move to the left along the green curve, I will be going up the surface. So I'm getting higher and higher. Whereas if I'm still at this point, and then I move to the right along the green curve, I'm going to get values that are lower. So because the black curve in the plane and the green curve in the plane cross each other, then I know I'm not at a max or a min. So when I am at a max or a min, they can't cross each other. So for example, I'd have to be at a point like that, where they don't cross each other. They're tangent to each other. And you can see up on the surface now that we're sitting at a maximum value on that black curve. And that's precisely when I'm sort of not quite at it, I have to nudge it by a little bit, but this is essentially when the gradient vectors are parallel to each other. Let's see if I can nudge it. I probably can't get the degree of accuracy I need without going and really manipulating the values. But that's the idea, is that I'm at this point, the level curve and the constraint curve are tangent to each other, and that corresponds to a maximum or a minimum. And if I go around to the other one, so here I'm at a minimum on the surface. And again, you can see that the gradients are parallel to each other. And again, I'll go to a maximum on the surface. So we'll keep going. Maximum somewhere around here. Kind of hard to nail it down precisely, but there's a maximum up on the surface, and again, that's where our gradient and our gradient of our level curve, our gradient of our constraint curve are parallel to each other. So that's the idea with Lagrange multipliers. Look for the places where the gradients are parallel to each other, because those are going to give you the max and mins. So let's have a look at the method in general, and then we'll do an example. So the method is, we have a function, little f, that we want to find the maximum or minimum value of, given that our inputs are allowed to come from a constraint, g of x, y, z equals k. We need to search for places where the max min can occur. That are going to be the places where the gradient of f is parallel to the gradient of g. If we unpack that into its three equations for each component, then we get those three equations on the left. And then we have our constraint curve. X, Y, Z also has to satisfy that. So X, Y, Z has to satisfy these four equations. And if it satisfies these four equations, then that's the possibility for having a max or a min. And then we can go ahead and compute the function value, see which one's biggest, see which one's smallest. So this is our technique for finding max and mins of functions given a constraint, is we solve these, in this case, four equations in these four unknowns, x, y, z, and lambda. So let's go ahead and do an example, a familiar example, one we already know the answer to because we just did it using the techniques from 14.7. So what do we have? Well, we have our cost function. This cost function is the same. This is the thing we want to find the max or minimum of. So that's 5, and again this was x, y, and z. So that's 5xy plus 2xz plus 2yz. And then we have our constraint. And our constraint was our volume equation. It was x, y, z is equal to this constant v. So we can call this g of x, y, z. That's our constraint. G of x, y, z is equal to a constant. In this case, the constant is v. So there's our setup. We're not going to solve for one variable in terms of the other and reduce the optimization problem to a new one in less dimensions. We're going to use the method of Lagrange multipliers. The method of Lagrange multipliers says, look for the places where the gradient of the cost is a multiple of the gradient of the constraint. And so let's go ahead and write those things out. We've got c sub x has to be lambda g sub x. C sub y has to be lambda g sub y. C sub z has to be lambda g sub z. And we've got our constraint equation. X, y, z has to be v. So the key takeaway here is we've got 4 equations and we've got 4 unknowns. What are our equations in this case? C sub x, so the derivative of c with respect to x is 5y plus 2z is equal to lambda times g sub x, so that's lambda yz. C sub y is 5x plus 2z is equal to lambda g sub y, that's xz. C sub z is 2x plus 2y is equal to lambda g sub z, so that's lambda xy. And then we've got our xyz is equal to v. So these are our 4 equations. 4 unknowns are x, y, z, and lambda. V is not an unknown. V is our fixed volume, whatever it may be. Some fixed volume we need to have. So V is a constant. The unknowns are x, y, z, and lambda. So we got 4 equations and 4 unknowns. The problem is these 4 equations are not linear equations. If these were 4 linear equations and 4 unknowns, then we'd just have techniques from linear algebra that could say, oh, we know how to solve these kinds of equations. But in general, we're not going to get linear equations. These are going to be nonlinear equations, and we don't have a technique that will work to solve systems of nonlinear equations. We basically have heuristics or ad hoc methods, or basically, in short, whatever we can do to get it to work is what we do. So in this case, it really depends on the nature of these equations. How do they look? How do they relate to each other? Can we do some sort of algebra that will allow us to solve them? And so in general, there is no foolproof method that's going to allow us to do this. There's a bit of an art to solving these things. Exploit patterns. See if you can come up with a value for x, y, z, and lambda that satisfies all 3 of these equations. So what are we going to do to solve these ones? Well, I'm going to notice that each one of these involves a lambda and 2 of the variables. So what that means is I can multiply the first equation by an x, because that right hand side is missing an x. If I'm thinking of it lambda yz, it's missing an x. So I can multiply through by x. That gives me 5xy plus 2xz is equal to lambda xyz. The second equation I get by multiplying the y partial equation by y. That's 5xy plus 2yz is equal to lambda xyz. And then the third equation I'll get by multiplying through by z. 2xz plus 2yz is equal to lambda xyz. And so now I can say things like, well, equation 1 has to equal equation 2 because they're both equal to lambda xyz. So I have 5xy plus 2xz is equal to 5xy plus 2yz. The 5xy's would cancel off. I'd also get that canceling the 2's. And so I get that xz is equal to yz. And since xz is equal to yz, that tells me that either z is equal to 0 or x is equal to y. Can z be equal to 0? Well, if I go back up to the volume equation, the constraint equation, xyz has to be v, so z can't be 0. Because if z was 0, the volume would be 0. The volume is our fixed constant. We're trying to make this aquarium, so we're going to assume that it's a non-zero volume. We're trying to make an aquarium with non-zero volume. So I can't have z is equal to 0, which means we know that x has to be equal to y. I can also take equation 2. That's got to equal equation 3. So we have that 5xy plus 2yz is equal to 2xz plus 2yz. And again, we've got the 2yz's cancel. This tells us then that 5xy is equal to 2xz. Can x be 0? I'd really like to just divide both sides by x, cancel it off, or multiply by the reciprocal of x. And I can because I know x is non-zero. Why is x non-zero? Again, for the same reason z is not 0. If x were 0, then the volume would be 0. So because x is non-zero, we have that 5y is equal to 2z, or in other words, z is equal to 5/2 y. And there we go. We have that z has to be 5/2 y, and x has to be y. So we have this relationship between x, y, and z. However, we need to find specific values. And so what we've done is we've used the gradients being parallel to each other, but now to finish things off, we can take these two expressions and plug them into our volume equation. And that tells us that, I've got x times y, but y is also x, times z, but z is 5/2 of y, but y is also x. So we get an equation that looks like x times 5/2 x is equal to the volume. Or in other words, x cubed is equal to 2/5 v, or x is equal to the cubed root of 2/5 v. So that's worth celebrating because now we have a specific value of x. And so what we have is that, therefore, x is equal to y is equal to the cubed root of 2/5 v. And so z is equal to 5/2 of y. So it'll be 5/2 of this expression, so that means z is equal to, a little bit of simplification, we'll get it to 25 over 4 v to the 1/3, or the cubed root of that. And so there we go. We found our x, y, and z. And the thing to note is that these values are precisely the values we got when we solved it using the techniques from 14.7, converting it to a 2D optimization problem. So here we did the Lagrange multipliers method, where we said that the gradient of the function we're trying to optimize has to be parallel to the gradient of the constraint. And we used that to set up 4 equations which we solved and ended up with the same solution. Now we'll look at a few more examples in this section. I'll split those off into different videos, and you can watch each example in any order you want. I would suggest trying them first from the lecture notes. Try the example first, and then go ahead and see how I do them in the video. And so I'll split those up so you can do them in any order you like. All right, thanks for watching.